Hello, everybody. Thank you for coming. I appreciate that. My name is Julian Voss-Andreae. I'm going to talk a little bit about my work and where it came from, what you see here. I made the piece outside, and these are images of other works. Okay, so I'm going to start with a double slit experiment, which is how I always start my talks because it's so fascinating. And that's where I come from. So my background is in physics. I studied experimental physics, and this is an ancient experiment. It shows basically, I need my both hands for this. It shows that if you have two openings in a slit and you have a wave going through those two slits, then in the middle they do this, so you have a lot of light there, and right next to it they go like this, so they cancel each other out, the two contributions, so there's nothing to see. So that's the standard experiment 1802 that shows light is actually a wave. Turns out later light is also a particle, so there's many variations of this experiment. And it turns also out that particles like this jacket here, for example, or these human beings here, or what they're made of, is also a wave. So what my graduate thesis was about was an experiment that took a pretty big chunk of matter, in this case a Buckminster fullerene, carbon-60, shaped like a soccer ball, and subject that through this double slit setup. And what happens is the same thing. We see, that's the setup. It's a little more complicated than just with light, as you can imagine. In fact, that's the setup there in reality. That was 1999. That was the team back then. Maybe you can recognize me. I look a lot younger 20 years ago. And so that's the experimental outcome. So we see in the middle is the peak I was talking about, where a single buckyball, what's measured or detected as a buckyball, has been going through two openings at the same time, magically somehow, then interfered with itself to do this. You see a lot of buckyballs right in the middle, and right next to it, it somehow interfered with itself to not be there. And it's less likely to be detected there. So that's really strange. And that's like a key experiment to see just how bizarre the world is, that we think is actually easy. We think this jacket is here and not there, but in quantum physics it's all different. So that was really intriguing that long ago for me. Now it's still intriguing. That kind of sums it up pretty well. 1940, Charles Adams. You know, we detect this one particle, but something is really bizarre on the way. So when that was in Vienna, and my job was to, after this experiment was successful, to look into biomolecules. Basically, we want to eventually send this person through the double slit, you know, to see how would that feel like. And the next step from a buckyball to a person is maybe a protein. We were thinking a virus at that time. We thought, naive as physicists are, we thought viruses are same symmetry like a buckyball, so it should be pretty simple. Turns out the smallest virus is like 30 times bigger than a buckyball, and it's basically impossible with the experimental stuff we have these days. So the next step was to go into proteins. Proteins are the building blocks of life. They are chains of amino acids that wind into space in specific configurations. And at that time, I met this woman, and she, in Italy, there she is, and she's a neuroscientist. At that time she was. And I asked her, so what would be a molecule that we can image, like a protein that we can image well? And she's like, have you looked into a green fluorescent protein? And I was like, never heard about this thing. And turns out that's a protein that's encoded by a piece of DNA in a jellyfish. So it makes certain jellyfish glow green in the dark, actually out here in the Pacific. And you can take that DNA that encodes this green little lantern, and then you can stick it into a bunny, for example. And then if you shine UV light on the bunny, that's how he looks like. He glows green, literally. It's true. And so this molecule has been used a lot in research, including Adriana's research. And that was the beginning, and I fell in love with her, and then came to Oregon because she was here, and that's basically why I'm here. So much for green fluorescent protein. Sounds boring, but it's fascinating. So then I came here and I enrolled in art college, and one of the first classes we had was, one of the first assignments in sculpture was, and I have to say sculpture at that point had not interested me really, but that changed very quickly because we were tasked with taking a piece of lumber, like square lumber, and cutting it into compound mitered cuts. So if you have a picture frame, for example, I don't see one here, but you do a 45-degree angle, flip it, and then you have a 90-degree, corner. You can do the same in 3D as you see there. And so when we made those little sculptures, I realized that's exactly what nature does. When nature goes from one-dimensional DNA, what that encodes the information essentially, it turns it into these chains of amino acids, and they wind into space. And so I realized I can take spatial data from proteins and turn them into cutting instructions to make mitered cut protein sculptures. And that's how I kind of got all into like sculpture. This is an early piece. That was an attempt to make a green fluorescent protein. And I was getting a little cocky. I thought, I can do this. Now, I wrote the software. I know how to do it. So I made another one at the same time. And turned out it was a pile of junk at the end. I couldn't assemble it. It was just the cuts were not accurate enough because of the one-dimensionality. It adds up, and also the joints weren't strong enough in wood. So I had two pieces of parts, basically. And the nice thing about science is in science you would scrap it and never could publish a paper. In art, you can put it on the gallery floor and call it failed protein biosynthesis and call it a piece of art. And so that's why I was like, that is cool. I need to get into art. So and because of that, I had to learn welding. I realized the only way to hold up against gravity is I need to make it out of steel. So that's my first steel piece. That's based on a small, like really strange molecule, a protein from an African herbal medicine that's used in Zaire by the people who are indigenous there to when labor slows down in childbirth, they give a tea made out of that plant, and that molecule actually accelerates labor again. And then I finally was able to make my green fluorescent protein. That's already the second version. That's now at the place where the GFP, this protein, was discovered. That's on San Juan Island, not too far away from here. Then I got into cutting up trees. I realized there's this one repeating motif in proteins that's called the alpha helix. And I thought, I want to do that. So. And then I understood that Linus Pauling is from here. He's from Portland, and he was the guy who discovered the alpha helix. And so I reached out and tried to find people who would be interested in maybe making like some sort of something to memorize him, like a sculpture to celebrate his work. And I found people, and so my student work one part of it was to make a big piece. Here I am welding in the studio and grinding. So I took a piece of square tubing, used to make a skyscraper, for example, and cut it up into those mitered cuts, and then that's the piece on Hawthorne you might know. And that's since 2004. So that's where that came from. That's the structure of an alpha helix. Then a little later, I made probably the most ambitious protein piece at that point. There's this amazing molecule called the antibody. It's a key molecule in our immune system. It looks like this. It has not just a few, but over 1,000 amino acids, so it's pretty tricky to make. And I was intrigued by the analogy between the human body and the human antibody. It's kind of bizarre. It's of course scaled to that size, but it's not in any ways distorted. So that's actually just superimposed like this. And the funny thing is, these two arms there, they actually do this too. They have these hinge regions in this area. So it's made to grab onto pieces of a virus, for example. And that's how your immune system recognizes these things and tags them so they can be destroyed, so you can enjoy yet another day, the next day, because otherwise we wouldn't. We would be gone right away. That's the three-dimensional structure. So from the idea, I wanted to use the analogy to the Leonardo guy, and so I kept the rays as today pointing at where the head would be if it was a human. That's the design. And then, of course, the big real problem is, how do you make this thing in real? In this case, we printed a two-dimensional stage. X and Y was taken care of by this image. I put in these posts so to take care of the third dimension. And that's kind of like an early attempt of how do you figure out to actually build these things in real. And it's been an ongoing really challenge and struggle, and exciting one too, because you have so many engineering problems. There's the piece, 12-foot diameter ring, that's in my old studio. That's the piece installed. That's in Florida at the Scripps Institute there. They opened the new campus at that time. This is a later protein piece, 2013. That's at Rutgers University. And it's funny that when I started making these protein structures, I reached out to scientists, and I found these people this institute where they house all the structural data. And that's like the incredible depository of all these like data, which I just love to just browse and think of proteins. I could make sculptures. And so at that point, they reached out to me because they finally had a building that actually was associated with this whole protein research, and then they wanted a sculpture there. And so I used the data from them to build the sculpture. And that's a 20-foot tall piece based on the collagen molecule. Collagen is, as you probably know, this most abundant protein in the human body. It's like mostly the structural aspect. Like it looks like a coiled rope a little bit. And so I took the 3 strands and gave them each a different color with glass, kind of to show how the different strands in this kind of research kind of, contribute to the synergy of finding new things. Then just as a side, that's a piece I did a little later, which is kind of funny to me because the people who commission it, actually, they're not into proteins. They don't even know it's a protein. For them, it's a modernist sculpture. But, and for them, it's totally abstract. But it's actually the opposite. It's based on something real, which is, I think that's kind of cool. It's a very unusual protein, which has this like loop at the end, and then the tail goes through it. It basically is used by certain strands of E. coli to screw up the synthesis of other proteins in other bacteria to kill them, because the topology is so twisted, it kind of puts them in a knot, basically. Back to Buckyballs. Any protein-related questions at this point? All right, Buckyballs. So that's the structure. I mentioned quickly in passing the soccer ball. This is an old structure known in mathematics since Aristotle. It's called the truncated icosahedron. It's if you take an icosahedron and chop off the corners, then you get that shape. And since that's a Leonardo drawing, by the way. That's the earliest picture we have of this with the open faces. And that was inspiring me when I made my first piece out of college in 2004. I took a piece of bronze sheet and cut out the hexagons and the pentagons, and I wanted to have an open face. So I cut out another set of them, and then another set. So I nested them all inside and hold them together with 60 spokes, if you will, pieces of bronze. At that point, that was really especially intriguing to me because this structure echoes pretty much the mathematical wave function in our experiment. So we have concentric circles of wavefronts, basically emanating out from one point, which is the mathematical description of this buckyball experiment I was describing. So then of course I need to challenge myself and made them bigger and bigger, and that's the biggest one. That's 30 feet diameter. What you see there is one hexagon out of 20. And there's 20 hexagons, 12 pentagons. I forgot to mention, it's this buckyball, the carbon-60 structure in that shape is only known since 1985. We knew diamond and graphite for forever, basically for millennia, and only very recently then people started understanding that there is another closed shell structure of graphite, of carbon, which was really exciting at that time. So that's why the buckyball is so popular, because also it's beautiful. So that buckyball here, that's the second time I built it. The first time around, I tried to build it and then hit a branch so it could support itself, but then gravity kicked in and I was almost not able to do this. Second time around, we were a little smarter. We built this giant scaffolding, 40 foot on each dimension, and then started from the top and then built it down and dismantled the scaffolding at the same time. Here's the buckyball from the side. And there's when you go under it. So actually it hovers like in the air. It's over like a creek. So you can go under it and look up. And that's this view. So then when I was contemplating the buckyball, I was asking myself, why do I like this so much? And I was so intrigued with this shape. And the answer came at Starbucks. When one of my kids at that time, I'm kind of a pretty harsh father coming from Germany, so I don't give them a whole milk, this sugar sweetened stuff, so they have to share that. So they get these gigantic plastic cups, and then they to make it bigger, they bubble it up like this. And that's what she's doing there. And when I looked at the plastic, that's exactly what a buckyball looks like here. If it's actually, the buckyball is an example of a very symmetric foam structure. And so I got all into foams because I was asking myself, what is a natural way of going from two-dimensional foams into 3 dimensions? Because that would be interesting to make a human like this. And so that's a recent spin-off where I solved the problem in 2D, which is easy. In 3D, it's really, really hard. In 2D, it's easy enough to make security screens like this. That's in my new studio. And in 3D, that's a really simple approach. You just take water balloons and then put something that hardens, like resin in this case, and pop them. And then you're left with the foam structure, essentially, because they want to minimize energy together when you squish them. But that didn't work out. I tried many things. I'm just showing some images that never went anywhere. So that's a little 3D printed metal form with polystyrene foam, polystyrene balls that make styrofoam, basically. So that makes this pregnant woman out of styrofoam, and then you can do a micro CT scan and look at the foam structure inside. And I wanted to use that as a sculpture. It turned out it was not very beautiful because it was not a happy equilibrium foam. It was more like a fake foam, so I discarded that. Then I found this paper where people took shaving cream, basically, and then did a super high resolution CT scan with that. So I made another little mold, this time this big, and filled it. Shaving cream didn't work for some reason. I'd used polyurethane foam. Here it's cut open. And I made this piece that also didn't really do the job. But I'm going there. I'm talking about this the whole time because that, by the way, is an example that I forgot to have in the slideshow of where this is fully calculated 3D foam. But it's still not a human being shape. That's where it's hopefully going next. But all this research made me look into things like how computers encode solids, for example, in this case, human beings. And then it's really easy to tap into the world of mesh processing and meshing algorithms. And that's like a whole world in itself. And I was getting really intrigued by that. And so that's one example that came out of that. You can just reduce the size and use algorithms as a raw material to do designs. In this case, a person made out of triangles, or a bigger person made out of triangles. That's a piece for Texas Tech. It's for the plant sciences department, and she's holding an agave plant between her hands. Also the triangle idea, but in this case, I took each triangle before we welded together and slumped glass into them. So that's why it looks a little bubbly. Then I realized I wanted to make this in doable. The glass bubbles had the disadvantage that if you transport the piece, it will basically self-destruct. So I had to actually on the truck, haul it upright all the way to Wyoming to install it. And so I didn't want to do that again. So then I had the same aesthetic idea, but I wanted to do it very differently. Instead of taking laser cut triangles of steel, I basically designed the whole thing in the computer, and then with the emergent technologies of the last few years, I was able to cast it in bronze and put windows in from the outside. That's a close-up of that. And then another spin-off of this triangle idea is, so what happens if you take triangles and turn them into 3D? It's the natural answer is also in engineering pretty ubiquitous. It's a tetrahedral, kind of a space-filling tetrahedral thing. So talking about the scientists and engineers, so in this case, there's a whole community that turns solids into tetrahedral stacks of irregular tetrahedra that are space-filling, so they're all connected. The reason is that when engineers want to calculate anything that's complicated, like most things, then they do that, they cut it up into all these little tetrahedra so they can solve their differential equations on this whole thing. And if it's doesn't look quite right, they just make them smaller, wait a little bit longer for the result, and then they get confident, okay, that's actually what happens here. So they can take a piece of steel and twist it, or they can shake it, and see resonances, which you couldn't see in the old methods by just using the pencil. And so I took these algorithms and let them run on my geometries and see what happened. What would happen if I space fill a human being with tetrahedra? And that's what happens. And that's from today, actually, photo. So the same tetrahedral idea, but instead of doing it in the computer and 3D printing and casting in bronze, that's an idea of taking each tetrahedron, cutting it out of steel, and in a way that it comes with hinges. So we flip them over and weld them shut. So we have over 1,000 tetrahedra, and then stack them up like physically. And with a computer and some marks on the tetrahedra, so we know how they go together. So it's kind of like a giant puzzle again. And then these are just the legs, so that's what we're building right now. It's been ongoing for 2 years. It's kind of the project that's on the back burner, because it's so insane. But I think it's going to look cool at the end. So then another side chain coming out of that was a body of works where I took the triangles and did what mathematicians call the dual. It's basically how an icosahedron is related to a dodecahedron. So you can flip them back and forth. And if you do that, but don't do one step, then you get something like this, which again resembles very much a foam, which is so interesting to me. And that's that piece where she's living now, next to this little spa, which is kind of neat because it mirrors the color and the shapes that you see in the water. Then another piece in that style is for private commission, where they had this big rock in their yard. So I took a few hundred photos of the rock and then made a 3D scan out of that. Then I took the top surface of the rock, 3D printed it in my shop, put it on a piece of plywood, then placed an actual model on there, scanned her on the fake rock, and then made the sculpture, and then we put it on the actual rock. So that's a really neat thing, because you can now, today, with 3D printing and 3D scanning, you can essentially take the world, put something in there that fits exactly to that world, and then do it in any size. So that's really fascinating to me. So there she sits, and she fits like perfectly on this rock that has no clear geometry. That's one of my 3D printers printing a piece of that. So I made a little bigger piece like that. That was for Georgia Tech. There it is hanging, drying, because I'm trying to seal it with certain things. I'm always trying new things because something doesn't work. Those are all the parts in the computer together. I color code them so I know where I am in order to be able to even have a way of seeing through this thing. There they are in my truck as bronze cast pieces. So the idea is you take cheap 3D printing technology, cheap as in like a few $1,000 that you can actually, that it's DIY type of equipment, not high-end stuff, and you can get it to a point that you can actually pretend it's like a wax piece and you do investment casting with it. So you put it into like a plaster shell, burn it out, and put molten metal in it. And so when that's doable, then suddenly everything becomes possible, because then you can take those metal parts and then weld them into any shape you want, and then that's a 6-foot tall piece. That's pretty big, made out of 150 of those little parts. And so that is actually the first piece I ever did with 3D printers. I went from the meshing algorithms and used that in specific ways to kind of just follow my ideas. In this case, like the broccoli that looks like this, the Romanesco. And it's intriguing because these algorithms do things, they optimize very often, which is very much what we see in nature. So that's why they look so familiar often, the results. That's another piece. Same underlying idea, in this case, pyramids. So she is like a she feels like she senses like all the electric fields, like a lightning rod. Then I was recently, that's a very recent piece, experimenting with geodesics along the that means the shortest distance. If you say if I want to go from my soles where I touch the ground, I go up and then I modulate that. That's kind of the image you get there. So and then finally to the body of works where this one is an example for. Now it's raining. So the idea, as I said in the very beginning, is we want to eventually send the person through the double slit, and so that's where the idea came from. I looked at what would the mathematical object look like of that person. So it turns out if I walk, then I would, as a quantum object, consist out of wave fronts that are perpendicular like this to my direction of motion. So that's kind of a simple thing, and I just kind of almost like for fun made this piece, an 8-foot tall, of this walking person out of these wave fronts by just cutting it out of steel. And there's another, that's a bronze version and a stainless version. There's one there, I promise. It's not photoshopped. It's hard to see. This one is in Wenatchee, Washington. And that particular one was actually, instead of welded, it was cold connected with screws. So that's why it's ridiculously perfect. That's why that one really disappears. Then a few years later, I started using the direction of the gaze. When we look at somebody's eyes, then we have this very specific direction. So I felt this disappearing thing is so cool when I look at my walking guy And there's this one angle where everything is different, where he disappears. And I wanted that to be the direction of the gaze, which is like your intent, your focus. You know, if you're like you're experiencing the world and you direct your attention to something. And I wanted this to be the disappearing angle. And so I made a whole series of works, including this Buddha here. That was the first big one I made, where a man and a woman look at each other, but they never see each other. And that's a piece we just installed 2 weeks ago. That's where I tried something new out. There's a lot of light going on. I don't have good photos yet, but only the Instagram photos here. As you can see, there's 100 programmable LEDs under the base plate, and they can do all sorts of patterns, which is kind of an interesting challenge to turn that into something meaningful. And so we're cycling at this point through different colors and just try it out, how it looks like. And it's pretty fun. So I leave you with a little bit of footage of that. And that concludes what I had to say today. Thank you.